Good afternoon, ladies and gentlemen. I would like to present our paper Service-Based Semiconductor Manufacturing using the Digital Reference Ontology for Global Service Discovery. The authors are Patrick Moder, Noah Ramsey, and Hans Ehm from Infineon, Germany, and myself, Hartwig Baumgärtl from University of Applied Sciences, Ulm. In order to achieve a competitive level at the key pillars of Industry 4.0 revolution, it's important to combine enabling automation and information technologies in innovative ways. For instance, service-oriented architectures act as technological basis for middleware and enable communication, authentication, authorization, orchestration, and secure data exchange, hence the possibility to use available services in a meaningful way. Semantic web technologies, on the other hand, provide a metastructure that represents basic concepts in contextual way, independent of natural languages, syntactic expressions, and subjective interpretations. When combining these technologies, the complexity even increases. It's hard to communicate and align between experts of the different technologies. To overcome this risk, the paper on hand illustrates a specific application scenario. We use the Arrowhead framework as SOA and a developed semiconductor manufacturing ontology as semantic model, together with a software application that maintains the ontology and provides the services to use. We show how we model the semiconductor manufacturing domain as ontology and how this representation is used as data repository for a global service discovery approach. This enables the retrieval of services even if different syntax is used. We actually extend the SOA and data exchange standards beyond their locality limits, as we achieve the global inter-enterprise service discovery approach. The agenda of our presentation is as follows. First, an overview to our application domain, semiconductor manufacturing, will be given. Next, we introduce the Digital Reference Ontology, before we present our approach and findings on ontology engineering. The ontology section is completed by an introduction of our domain ontology. In point 5, we give a very short introduction to the service life cycle of service-oriented architectures. Next, we present the Digital Reference Platform Application, a software that maintains the DR ontology and is integrated with Arrowhead framework. This software plays a central role in our application scenario, which is explained afterwards. The presentation is rounded off with a conclusion and an outlook. In general, semiconductor manufacturing is organized as shown on this slide. There are two main process areas, front-end and back-end processing, which are decoupled by a wafer stock, the so-called die bank. It starts with a wafer, a silicon disk of 200 or 300 millimeters of diameter. During wafer fabrication, several hundreds or thousands single chips are created and built up on a wafer. This requires up to 1000 processing steps and may last up to 90 days. Next, the wafers go to wafer test, where each single chip on the wafer is tested in 10 to 15 steps in further 4 days. In back-end, wafers are taken from the die bank, singulated, bonded, and encapsulated, and finally tested again. It's important to note that long cycle times require sophisticated planning processes, that cleanroom production is very capital intensive, and that the processes are conducted by globally distributed fabs and plants owned by manufacturers themselves as well as manufacturing service providers. The front-end process builds chips on the wafer layer for layer. Each layer is built by a sequence of processes like chemomechanical polishing, lithography, etching, deposition, doping, cleaning, and control. The key process in front-end is the lithography process. It allows the transfer of designs via masks to the wafer. The chips on the wafer may consist of up to 35 layers. That is, all processes here may be iteratively repeated up to 35 times. This may explain the long lead time in front-end. Opposite to that, back-end process is a more sequential process. It starts with the wafer material from the die bank, as we can see here, goes to the sawing of the wafer, to the die attach and the wire bond process before we go to the final test. We see a test equipment in backend here. After test, we will go to mark, scan and pack, which brings the chips usually in packages like tubes, trays, and tapes. But there are alternatives to this processing sequence. As we can see here, for specific types of products, for example chips, which don't have these legs as contacts, but small balls arranged in a ball grid array, bonding and encapsulation in the classical lead frame process may be replaced by a process called extended wafer level ball grid array processing. This is a specialized process and is conducted by very specialized service providers. Supply chain planners that use the supply chain and plan the supply chain according certain production sequences have to know about all these alternatives and the specific appropriate service providers. Let's now have a look to the Digital Reference Ontology. This ontology is developed to model semiconductor supply chains as well as supply chains containing semiconductors. And as you can imagine, it's a very large, very complex ontology. Each circle in this picture represents a class in this ontology. The dark blue ones are classes from imported other ontologies. The bright blue ones are classes from the DR itself. To organize such a huge ontology, we borrowed the concept of lobes from the human brain. And you see on this picture several of the lobes of the digital reference. On top, some of the imported ontologies in lobes like supply chain, organization, planning, and time, and product. And some more DR-specific lobes like semiconductor production and semiconductor development. Now I'd like to introduce two of the major challenges that we face during ontology engineering. The first challenge is the domain definition. The goal of the development is to achieve an industry-wide standard overarching company borders. This requires the consideration of different points of view in order to lead to a preferably generic definition of concepts that drive the industry. We approach this challenge by involving interested partners, for example different tiers along a semiconductor supply chain, and maintaining openness to various perspectives, for example academia or industry. The second challenge happens when, at a certain level of detail, definitions may divert to among the participating parties. We suggest an iterative process that determines a baseline, separating generic from specific concepts depending on their level of detail. The presented ontology includes an extensive domain landscape and covers various levels of abstraction. Its modeling can be basically approached from two different directions. The top-down approach determines the most generic concepts first and increases the level of detail. However, it's limited in case various data sources contain information regarding the same concept, which then requires effortful and error-prone mapping procedures. In the bottom-up approach, we define concepts for certain use cases in a structured way in order to rapidly achieve the desired results defined by the use case limits. However, many use cases within the same domain may overlap, which requires thorough and effortful cross-checking. Hence, we suggest a mixed attempt that combines both approaches. In parallel, we define generic concepts to achieve broad acceptance, while we identify use cases and apply the approach to visualize results early, which, especially in early stage, enables continuous improvement and user awareness. On the next 3 slides, I would like to show you very shortly our semiconductor manufacturing ontology. Let's start with the hierarchy view. We have several hierarchy levels to describe the process of manufacturing in semiconductor. As we have seen, there is a front-end process and a back-end process, which we call main processes. They are divided into several sub-processes like wafer fabrication and wafer test in front-end, or chip singulation, assembly, and final test in back-end. One challenge in modeling this ontology was to correctly handle the interleaved class hierarchy, which is represented by an is-a or subclass of type of relationship between, for example, a front-end process and main process, and wafer fabrication and sub-process. Both are classes. On the other hand, hierarchical decomposition of processes cannot be modeled as a taxonomy or class hierarchy, as a subnode here does not represent a specialization but only a part of the ancestor. So in our resulting ontology, we had to use the concept of having a class and an individual with the same name and the same IRI for each process, activity, and operation to model both the taxonomy with the is-a or subclass type of relations and the part of or has part type of relations for the hierarchical decomposition. In this picture, we see the process hierarchy classes, some samples of the activity classes, and some resources, and one more important relationship between resources and the processes. There has capability relationship with its inverse, the is capability of. This connects resources with processes. The resources have also an own hierarchy in this ontology, which is shown on the next picture. We see the semiconductor supply chain levels here, like customers, retailers, manufacturing companies, suppliers, and equipment suppliers, where the manufacturing companies are further divided into semiconductor manufacturers, like Infineon, and semiconductor manufacturing service providers like UMC. All companies operate and own plants. Each plant has one or more sites. This could be continued. The sites have work centers, and the work centers consist of machines or tools. These are not shown in this picture, but they are, of course, contained in the ontology. But we see on this picture again some examples for sub-processes, and again the relation between the activities or sub-processes and the resources that has capability relationship, which will be later used to identify appropriate resources and their owners for certain queries for capabilities. Let's now jump to the service-oriented architecture. Each service in the service-oriented architecture has a life cycle, which is, for example, shown by Cardoso and Chet in their paper. The life cycle consists of the phases description, advertisement, discovery, selection, composition, and execution. As these authors show, several types of semantics can be used during the different phases of the life cycle. Unfortunately, typically only semantic service descriptions occur. They use, for example, OLS, a specialization of the web ontology language OL, used for semantic service description. But there is no more usage of this semantic service description than to put them together in several ontologies. On the other hand, for advertisement discovery, typically only names and maybe some parameters with values are used for advertisement discovery. That means service discovery relies today mainly on a syntactical matching of service names given by a service requester and the service names registered in any service registry. Our claim is that semantic service descriptions put it in an ontology management system can be used for advertisement and service discovery as well, as we will show on the next slides. To do this, first we introduce the Digital Reference Platform Application, the DRPA, which is in fact an ontology management system. It was developed in the European research project Productive 4.0. The DRPA is a tool designed to explore the DR ontology by providing graph and tabular visualization and generating and storing data compliant with the DR. The ontology can be extended and updated both manually by user input and automated from Arrowhead repositories. Additionally, it offers an API for accessing its repository information via Sparkle queries and an export mechanism to add repository data to other repositories like the IoT catalog. As we can see here, the DRPA is designed according to the model view controller pattern for web applications. This design deviates from traditional pattern in the sense that the model is only updated by a controller and the viewer accesses the model only via the controller. The DRPA is embedded in an Arrowhead local cloud and, when launched, registers its services to its local service registry. Of specific interest for our scenario are the services for data input from Arrowhead service registries and service producers, which we call the Global Semantic Service Registration Service, and Sparkle API and Sparkle queries for specific services and their service producers, which we can see as the Global Semantic Service Discovery Service. Once the DRPA in its local cloud is launched and active in the Arrowhead network, an cyber-physical production system, for example a semiconductor fab, can register its capabilities as services at the DRPA and, by means of this, advertise its services. For that, the production system first has to ask its local service registry for a service that allows global semantic service registration. The service registry is informed via the Arrowhead infrastructure by this service registry via a global service registration mechanism about this service and answers with the address of the DRPA in its local cloud. Based on that, the Semicon fab sends its capabilities as services to the DRPA. The DRPA adds the service producer and its capabilities as individuals to the appropriate classes of the ontology and acknowledges the registration. Based on that, now a supply chain planner can act as a service requester and ask the DRPA for one or certain possible service providers or producers for certain production steps it needs in a specific supply chain. For that, the supply chain planner again asks its service registry for the address of the DRPA, and after the service registry answers with this address, the supply chain planner sends a Sparkle query to the DRPA. The DRPA resolves this query and answers with the corresponding service producers according to the query. Let's assume this supply chain planner is responsible for a supply chain of an existing product which uses the extended wafer level BGA processing step, and the current service provider for that is located in a country which is by accident affected by the COVID-19 pandemic. Let's say Taiwan. Now the supply chain planner immediately needs to reorganize the supply chain and exclude any fab or any provider located in this specific country. Then they could send a Sparkle query like this to identify further service providers which are capable of conducting the EWLB process but are not located in a specific country. The Ontology Management System resolves this query following the object properties like has capability or is capability of and is owned by to retrieve the appropriate resources and their owners, and comes back with a data package containing the companies and the resources of these companies. This can be used by the supply chain planner as a starting point for negotiations or for sending out requests of quotes without having a time-consuming research about alternative service providers. To conclude, semantic description of services to be used for global service discovery described in this paper makes the very complex and abstract concepts of ontology-based service description and ontology-based global service discovery concrete and hence easier to understand for people who are not familiar with both technologies in detail. And it provides a blueprint of service description, service registry, service discovery, and finally service usage in many industries beyond semiconductor manufacturing. This paper fosters the general understanding of solution approaches for general industrial problems in the age of digitalization with all described technologies. The concrete systems like Arrowhead framework, Digital Reference Ontology, and Digital Reference Platform Application are real and find increasing use in practice. This paper serves as a conceptual description of the complement of semantic web and service-oriented architectures and provides insights into a potential application domain. It requires future research to test these implications in industrial settings. Digital reference will be enhanced successively by more industrial domains. At the same time, use cases and application scenarios will be tested based on the Digital Reference Platform Application. Thank you very much for your attention.